Okay, so presumably I'm on the way to Livermore now too. Those of you who came late, if you ask a question, use these microphones, try and make it near your face so that people can hear the question in Livermore, but otherwise get it out of the way and don't touch it because it picks up extraneous noise. So you've all got the syllabus now. As I say here, 75% is program assignment and 25% is a midterm, which I believe is, where's the date here? It's scheduled for Wednesday, November 9th. So there will be no final. Most of your grade is based on programming assignments. And there are a lot of programming assignments. I think people learn more by actually doing than just by reading the theory. But our book, this is the book, Advanced Global Illumination. I specified the third edition, so the third edition may be available in the bookstore. It probably is, but I'm not sure what they do for grad. No, I probably couldn't be, because I only decided a week and a day ago, or actually a week ago, to teach this course by popular demand. There were no graphics courses listed in the fall, so I'm teaching an overload this quarter. There was no time to get it from the bookstore, so you'll have to get it from Amazon or something like that. I remember in another course, somebody just sent me an email this morning, can I get the second edition, or in that case, or an earlier edition. This is the second edition. The first edition is equally good. The page numbers will be different, but the topics are basically there. If you buy the first edition, you can probably find the corresponding topics. Otherwise, I do have a copy of the first edition. I can even help you or put a previous syllabus on where I use that edition if I can find it, so that the page numbers correspond. So, you know, either one will be okay, but the page numbers I've listed for the readings are in the first one. I mean, in the second edition. So all the theory is in here, probably more than you want. So I've taught this course several times from many different books. And when I taught it, I think it was 2005 from this book, the students complained, too much theory, too much math. But when I taught it from several other books, like there's one by Sutliff, and then there's a really big fat one by, let's see if I can remember those authors. Two graduate students at Stanford wrote it while they were a graduate student. Sorry, I have a mental block against it, but it was done by what they call literate programming, where the program source was very closely tied to the text, and there were all sorts of links. And in both those cases, the text was describing a very specific software system that the authors wrote. And then for homework, I asked people to add to it. So the complaint at that point was that the details in those textbooks were too specifically oriented to their code base, and people didn't want to learn that much detail in a big code base. On the other hand, the preface of this book, or somewhere in the first chapter that I actually refer to in the handout, says that if the content of this course is ray tracing, by the way. We say distributed ray tracing, probably better called distribution ray tracing. It's not because it's distributed across processors, although it could very well be, because ray tracing can be done in parallel if you consider each ray independent. What it really means is we're using statistics like Monte Carlo simulation to try and figure out light bounces, say from the ceiling onto the floor, onto the wall, and eventually onto a piece of paper that may have indirect illumination. Say if it was this seat, which is under the table, is getting indirect bounce illumination. We have shadow penumbras. We have glossy reflections. All these effects that are sort of enhancements of the basic Whitted ray tracing for perfectly shiny surfaces or perfectly diffuse surfaces. So what I'm going to talk about today is that Whitted ray tracing. And the first assignment is going to be to implement it. But that means you would have to write a file type to describe the scene. You would have to write array, object intersection for each object type. And that's not really what we want to concentrate in this course. So what I've done is I've put a file of source code from somebody who, it's Steve Parker, who taught a similar course at the University of Utah quite a few years ago, and made the core part of his ray tracer available. It basically, as far as I recall, just does this basic Whitted ray tracing that's going to be part of your first assignment. And so you don't have to do, you know, the file reading and format. You don't have to do the basic ray object intersection, which I will talk about on Monday's lecture. But it's just, the first assignment is just to make that work. Actually, the last time I taught this course using it, it was in a different environment. When I tried to compile it on my Linux machine in my office, I couldn't even compile it. The right libraries, maybe it uses certain libraries that I forgot to put in the command line or something. So, you know, wherever you try, you'll still, it's got no makefile, for example. You'll still have to see what it needs, and like maybe it uses standard template library, I don't know. You have to make sure that you actually get it to compile if you choose to use it. You don't have to use it. You can start from scratch if you wish. I'm just trying to make it easier. So the first, I have to look at the assignments myself to remember them. The first assignment is just to make that basic ray tracing work. The second assignment is to add things like motion blur and depth of field and anti-aliasing, which aren't even discussed in our textbook, but were discussed along with things like glossy reflection in a basic paper that came out in 1984 called Distributed Ray Tracing by Cook, Porter, and Carpenter. And that paper really excited me because it showed that you could get all these effects just by this Monte Carlo sampling, and it really didn't take any longer than doing just one of these effects. And so we'll study that paper, and the second assignment will be to do those effects. Then, but not refraction. I put off refraction to the end of the quarter just because I want to get started on the global illumination. So the global illumination is things like shadow penumbras, where instead of point sources like you have in the Whitted ray tracing and even in the distributed ray tracing for the illumination, we're talking about area light sources like these ceiling lights. And that means the shadows aren't sharp. They depend on how much of the light source a given point on the surface you're shading can see. And that means that you need, is there one more of these left here? You got it. You need some computation which is going to figure out how much of that light source is visible. And also this multiple bounce of light, which is called global illumination. And so most of the course is concentrating on that, and most of the mathematics in the textbook is concentrating on that. Now, we have an option once we get, so the third assignment is doing the shadow penumbras, and it's called path tracing, basically, when you take multiple diffuse bounces off the surface to see, you know, what light is hitting the floor. It's coming from all over the room, and you basically got a sample with a bunch of extra rays all over the room. So that is the key content of the course, and that's your third assignment. And I believe that's all the set assignments. And then, the same time the third assignment is due, Monday, November 7th, I want a project description. So I want you to email me what you propose to do in a final project. And the final project will sort of go beyond this basic path tracing to do other things that might make it more accurate or more efficient or get more effects, like effects of smoke in the volume. I'll be talking about that at the end of the course, how you do corresponding things. There's various techniques called photon mapping, density estimation, irradiance caching, bidirectional path tracing, Metropolis, Monte Carlo methods. They go on and on. Many of them are listed near the back of the book. And I'd like you to do a final project, which I think counts more than the other homework assignments. And so I want a proposal on that, and so we agree on what you're going to do, and then you've got basically a month to do it in. I hope the final projects can be presented here. So I assume most of you have laptops, otherwise we can bring mine, and you can bring a USB drive to put a talk on. And so, you know, all you need to do is show the images and say what you did to make them. If you don't have powerful enough computers, or you choose to use the CSIF labs, They're in the basement of Kemper Hall. You're welcome to use those computers instead of your own. That's what my undergraduate course is doing. And the way I wrote this, I sort of took the boilerplate language that I told to my undergraduate class. You know, the reader has got to be able to execute your code in this lab. But then I had second thoughts about that, because really all I care about is your images. You know, if the images show the effect, that's enough for me. You know, if the images have some obvious glitch in them, I may be able to look at your code and find out where the bug was. So, like, if you use this package that I put online for you, you know, if you send me the routines that you changed, that's fine too, and I might want to look at them. But I'm probably not going to try and compile and execute it. So this sort of boilerplate language I made about make sure it's compilable on the standard hardware that I could use for grading probably doesn't apply for our course, so you can actually not worry about it. Which means if you want to use a Windows machine, just, I don't care. Just send me, in fact, you don't even have to use hand-in. If you, like the people in Livermore are working remotely, they probably don't want to use the hand-in facility. They just want to send me email with their source and their images. But I need to be able to view those images on my screen, and I'm going to use the Eye of GNOME tool, which means your images have got to be one of these formats listed here that tool knows how to do. So, you know, if you just want to use, you know, a screen view yourself created by some sort of OpenGL version that actually just, you know, takes your internal data file to your code and transfers it onto the screen with, you know, just copy pixels or something, then even a screen capture of that window on your screen would work to show me the image. Or you can, you know, all these file formats have tools to write them out from, you know, packed arrays of data. I'm sure you can figure out how to do that. I've had to do that at different times in my life, although I've forgotten it now. I'm sure they're all documented. Just pick one that I can look at. And then on the last day of class, I actually want you to bring me a printed out piece of paper with some images on it and a description of what you did, just so when I try and remember what you showed, I have some piece of paper to help me when I'm determining the final grade. Okay, so I left my office hours blank, but I gave my undergraduate students priority in setting them so it didn't conflict with their classes. So there are Mondays at 10 a.m. and 4 p.m. and Friday at 4 p.m. But I've also given you my email and even my home phone number and a phone number that I'm reachable at when I spend Tuesdays and Thursdays at Lawrence Berkeley Lab. So there are multiple ways of contacting me outside of office hours. And, you know, if we need to, we can set up another appointment time. So the last thing we have to decide, maybe not today, but let's get some opinions. I can also make part of the course after I finish the basic, you know, path tracing scheme that's going to get the direct, indirect illumination that you need for homework. We can do presentations of some of these topics. Some of them are in the book, and many of them are in research papers, and maybe some of them they're only just explained briefly in the book and in more detail in research papers. So we can spend time with students presenting the later material in class rather than me presenting it. And in that case, you know, the quality of the presentation can be part of the grade. And so less will count on the homework and the midterm. So we can take a vote on that, maybe on Monday. So think about how you want to organize the last part of the course. You know, you can look through some of those topics in the book, and the book's got lots of references. For each of the ones they discuss, they have the key papers there. And then I'll ask you Monday, and we'll revise the syllabus, depending on whether I'm teaching the later material or whether you're taking turns explaining it. The last time I taught this course with a midterm instead of a final, because you've got enough effort working on a nice final project. We don't need to make you study for a final too. But on the other hand, there's no way to test the material, the advanced material. So in the past, I also made unannounced quizzes. I think I'm not going to do this. I think you'll either read it or you won't, depending on if you're interested or not. It won't be necessary to do the programming assignments or for the midterm. I hope some of you keep attending. I guess if you're presenting, you'll at least present. And I hope the rest of you have enough courtesy to listen to your fellow students or to listen to me near the end of the quarter. But we won't really be testing that material. So it's up to you how much energy you want to put into learning it. I hope you're interested enough to do that. So are there any logistics questions? Any opinions people want to express right now in advance of our Monday decision, whether you want to present stuff or just have me present it? Well, I hope you get an opinion by Monday then, because I'm trying to let you decide that point together. Okay, so Turner-Whitted ray tracing, which is the simple ray tracing without the global illumination and motion blur and stuff like that. So what I'm going to do is contrast it to the Z-buffer algorithm. So here is the Z-buffer algorithm. And the outer loop is over objects. And then the inner loop is over the pixels inside that object. Strictly speaking, it's inside the object's projection onto the screen. If the depth of the object is closer than the depth stored in the Z buffer, which is initialized to some very far distance, closer than the Z buffer value, then you update. Well, I should maybe say shade. I'll just say update the color buffer with the object's shading. And update the Z buffer. I didn't copy this correctly. My stuff on my sheet said compute the object shading and then update the color buffer and the Z buffer. Okay, so now I want to show ray casting. That's without reflections. And the basic difference is the outer loop is over pixels. And the inner loop is over objects. And we have an if, I probably should indent that. If the ray through the pixel intersects the object, then, well, now this time I'll write it, compute shading color. Well, I guess what we want to say, and the intersection is closer. And the intersection is closer than the saved depth. Then compute shading and update color. So if we go back to the Z-buffer algorithm for a minute, what we do is we need to initialize the Z-buffer to be a very far value and the color to be some default background black color or something. And then this is a scan conversion step. Just find the pixels, like find the pixels on a line or inside a projection of a sphere or inside a polygon. So given the polygon, you only consider the pixels inside it. And then you do this depth comparison. But you need to store a whole Z buffer. In this algorithm, what you're storing is only one single color for the ray and one single depth for the ray. So it doesn't require the depth buffer storage. But you need a ray object intersection, which is harder to do efficiently than it is to scan convert a polygon, because this loop is saying you're testing all the polygons, and if you have a scene made of tiny little polygons, you're going to miss most of them. So there are various acceleration schemes that people use for ray tracing to try and cull just the polygons that are likely to intersect a given ray. And we're not going to talk about those at all, because this is really a global illumination course, not a ray tracing technology course. But you can use a KD tree or some other spatial data structure to only, and then you run the ray through the spatial data structure. It also could just be a division of the data into a grid, and then each grid cell has the objects that overlap that grid cell, just to avoid testing the ray against all the objects. So if you want an efficient ray tracer, you need to think about that. We're not going to talk about that in this course, and there's no need to implement it in your code. I spelled shading wrong, didn't I? So both of these algorithms could benefit by something called deferred shading. Sometimes the shading computation is very complicated, especially in the motion picture industry, where you have multiple textures for bumps and colors and grunge and dust and specularity and roughness, and they get really fancy with the shading. In fact, there are whole shading languages. RenderMan is one of them. So the shading computation can take a long time. And here, if we find something closer, we're going to redo the shading. Also in the depth buffer algorithm, we're continually computing the shading, and then something may be found later that's closer, and we're throwing that shading away. So one optimization is to save the information like texture coordinates, normal, color, and stuff. And then once you've found the closest thing on the ray, then you do the shading. Well, similarly, if we come back to the Z-buffer algorithm, if we had extra buffers to save that information, like the normal and the texture coordinates, we could actually do deferred shading for the Z-buffer algorithm too. And I think some graphics hardware implementations or programs can do it that way. Depends the trade-off. I mean, saving all that data takes memory for the buffer case. It's not so much for the pixel case, because we only have one ray at a time. But some people do deferred shading also in a Z-buffer context. Okay, so the reason I call this one ray casting instead of ray tracing is ray tracing traditionally refers to this scheme that was first done by Turner Whitted, I think in 1981, where he dealt with reflection off of shiny surfaces, refraction through glass, and shadows, all by ray tracing. Question? Yeah.
What class is this?
This is ECS 275.
Oh, okay. Wrong classroom.
So actually, before I do that, do I really want to do this? I want to talk about rays. Yeah. What is a ray? A ray is an origin, O, which is a position, and a direction, D, which is a vector. Actually, I should put a hat on it because it's a unit vector. And we have a ray equation. R of t is the origin plus t, which is a scalar, times this direction vector. And so if t is 0, we're at the start origin. If t is a half, we're here. If t is 1, we're at this unit vector direction. And as t increases past 1, we continue along that ray. Usually we only want non-negative t. And so the ray object intersection is basically putting this equation of the ray into, say, a parameterized equation for the ray, where t is the distance parameter along the ray, intersected, say, with an implicit equation for a sphere or a plane. That's what we'll do next class. And so if we have deferred shading, let's see, where will I? Let me go back to the beginning of the board here and do code for a deferred shading of multiple objects. So let's call it like first hit ray, and what we're going to return is a shading record at the minimum intersection, minimum T intersection. And so we have this shading record which contains all the information you need to do the deferred shading, probably the surface normal and color, maybe texture coordinates, 3D position, everything that you might need. And I'm going to the temporary, the one for the hit that comes back and the one for the minimum hit, which I keep updating instead of the color. Okay, and I have a double T, which is going to be the temporary one that I'm going to get by intersecting the object, and the T min, which is going to be the minimum intersection I've got so far. And I'm going to start it as some huge number. You know, as far beyond any possible object hit I would get. And then I just have, for say int j equals 0, j is less than the number of different objects. So I have if, say I have every object has a hit function. And what does that hit function has to return? Its input is the ray, and it's associated with the object, and what it returns is the distance where that ray first hit the object, and a shading record, which is the data you need to do this, what did I call it? Post something shading. You know, after you find the frontmost point, we're going to shade it. Okay, so, and T is less than the distance you've had so far, which you started out very far away. That means you found a closer intersection than any objects you've intersected so far. Then you're just going to update the minimum T min equals T and SR min equals SR. And then a pixel. Well, why don't I just say return? Suppose this returns a color. So return shade. So you have a routine that uses this SR min information to determine the color of the pixel. That's what this post-visibility shading is about. So I think I have closed brackets on this loop, and that's basically the detailed version of that code. Okay, so now let me draw a picture for what the Whitted ray tracing does. Say you have a room and you've got, say, a light bulb on the ceiling generating light, but we're treating it as a point source. You know, here are the walls of the room and the ceilings of the room. Maybe there's a table sitting on the floor. I'm going to draw everything in 2D here, so I don't have to deal with drawing full 3D things. But maybe this table has got some shiny spheres on it, right? And we want to get multiple reflection effect. So if our viewpoint is here, say, you know, we're going between the legs of the table and we hit the floor here. We want to know, this floor is maybe diffuse. We're not going to do recursive ray tracing on it, but we still want to know if it's illuminated. For the shading, we want to know, can it see the point light source? So we send what's called a shadow feeler to the light source. We see if we go from the direction of this hit point of the viewing ray. So one of the things you're going to have to compute when you set up a camera is for every pixel, you're going to get the viewing ray through the center of it, basically, from the camera point to this imaginary window that's got the pixels in it and make it a unit vector for the D vector. Now your origin point is at that hit point, and you have to determine whether the light is visible. So the light will be visible if the first object you hit along the ray is the light, rather than some other object like the top of the table. So again, you still need this object hit intersection point. Actually, you don't even need the shading value, because all you want to determine is the visibility. So sometimes people write two kinds of hit routines. One which takes the trouble to return this, and one which doesn't bother because it's being called just for this shadow field array. All you care about is the T. Or maybe if you're worried that the T might not be accurate, maybe an object ID. See if the closest point really is the light. Because, you know, if you have some sort of piece of paper pasted right on here, you know, maybe you're going to get some confusion just by the distance. You know, with floating point accuracy or something. Okay, so that's for the shadow effect. And for the light bounce effect, if you hit a specular surface, you're going to use the surface normal and make a reflected ray and see what that reflected ray hits. And then you're going to shade this point, you know, with its own shadow fielder to figure out what the shading is here. Then you're going to apply it. If it was a perfect 100% reflective sphere, it would just be that color. But it may have some less than 100% reflectivity, in which case you're going to have to multiply this color by the reflectivity. In fact, it might have dust on it, which is reflecting diffusely, if it's sort of been sitting there, you know, accumulating dust. So it may be a combination of diffuse term and a perfect mirror term, in which case you use the shadow fielder to see how much the dust is reflecting. You apply diffuse shading. You might apply ambient shading too. And then if it's specular, then you have the specular coefficient. Or the diffuse component might be 0, and you don't need to do the diffuse shading. Now this is called recursive ray tracing, because if you have a point like this, whose reflection is into this sphere, and then reflects into this sphere, and then reflects on the table, you've got to call the same shading function recursively to get the contributions from all these bounces. So in the 15 or 20 minutes left, I want to write a sort of pseudocode for that kind of Whitted recursive ray tracing, which is going to be what you're going to have to implement for the first assignment. So again, it's going to be a color. So why don't I call it ray color? And the input, again, is a ray. So, and I'm going to start off by initializing the color is black. And then I'm going to add all these different components to it for diffuse, ambient, specular, and so forth. So I guess I'm going to call this first hit ray. But basically, I'm going to return the SR min. I've written it like here I just said, you know, you can return the color. But really, this whole structure is what we really care about. Because that's going to say the light that came in on the given ray, that we may have to combine it before we actually set a pixel color. So in fact, if I were doing it that way, I could have just quit with whatever SR min I got at the last intersection. I won't even need to color a pixel. Okay, and now I can say if SR min dot diffuse, if there is any diffuse reflection component, then we need to make a shadow ray. So the origin is the hit point. Right, this intersection needs the 3D coordinates of the hit point because you've got to draw the direction vector, if we move back to this board, from this hit point to the light source. Right, so we can say vector v, light source, position, minus, well, this is the hit point. And I need to, in order to compare the distances to see if my closest object is closer than it, I have a distance. Let's say the absolute value of v, right? It's the length of the vector. And the shadow ray, I should have had a dot here, right? This shadow ray record consists of two things, origin and a distance. A unit vector, I'm sorry, d for direction, and that's just v over its length, right? Well, I should over distance, I guess, since I've already computed it. And then I just call the light source. Wait a minute, what am I going to do? I'm going to just take this ray and I'm going to call, yeah, I guess I made a different, well, let's just say hit. What did I call this? Did I call it hit over there? Hit. For the first object, what am I? No, first hit. So we're calling first hit maybe the shadow variant that doesn't bother computing that shading record because we don't. I just said we don't need it. We just want to see if we get to the light source first. And so it's with this. What did we call it? Shadow ray. I guess I didn't declare these variables, but we need the t, and you know, we need it, or maybe we don't need it if it's a special routine that doesn't even have it as a parameter. All we care about is t. If t is closer than d, then we add the shading. So if, I guess it's going to be t is, say, greater than or equal to d. That means it should be exactly d, and probably, you know, floating point accuracy may not end up taking the ray hit function giving the same as this distance computation. So maybe we just better say d minus some epsilon to take account of floating point potential errors. Then we know that this light source really was the first object we hit. Or, you know, you might do an SR and put the object ID, and if it's a light bulb, that'd be another way to tell. Then you want to add the diffuse shading. So color, how have I divided it? Shading. With the properties of the light, maybe the color of the light information, and this SR min, the properties of the surface there. So that's diffuse shading. You might want ambient shading. If you have an ambient coefficient, you do the same thing. I'll say ambient contribution from whatever the shading information is. So this might just be Lambert's law, and this just might be ambient color, you know, formula for how much ambient light, and you have some ambient light that uses default or something for the room. Of course, that's what eventually is going to be the global illumination. Ambient is just an approximation of the global illumination that we're going to try and do for the rest of the course. And now, here is the reflection. So if SR min dot reflection So this could either be a float, which is the reflection coefficient, or just could be a logical thing that says whether you're actually doing reflection for that particular kind of surface. Then we have to compute the reflected ray. I'll tell you how to do that in a minute. I just want to finish the code here. And maybe you have to compute the reflection coefficient. Reflection. For surfaces like glass or water, the reflection coefficient depends on whether you're looking straight down into the water or the glass, in which case it doesn't reflect much, or you're looking in a very glancing direction, in which case it reflects a whole lot more. So it may actually depend on the geometry. And then you're going to add on the color is added extra, the reflection coefficient, times the ray color. Did I call this thing ray color? Yeah, ray color of reflected ray. So I guess I need some curly brackets here and at the end. And I left off refraction, but you could have the same if for refraction. So I'm going to tell you today how to do the reflected ray. I'm not including refraction right now, even though Turner-Whitted did, because I'm going to wait till farther into the quarter before I tell you how to compute the refracted ray and the refraction coefficient. But let me tell you how to compute the reflected ray. So I guess I probably shouldn't have erased this ray, but it's more common to draw a picture where the surface is horizontal, the normal is up. The viewing ray direction goes like this, and the reflected ray direction goes like that. And it's actually more common to look at the viewing ray toward your eye. So V equals sort of minus the viewing ray. This is just because it's the way I remember this formula. Because when you do shading, you usually think of a vector toward the eye instead of the vector of the direction that the viewing ray. Actually, the photons go this way. And the incoming photons that are reflecting go that way. But when we do ray tracing from the eye, we're actually tracing it in the opposite direction. Later in the course, we'll talk about actually tracing the photons from the light source when we do photon mapping. And when we do bidirectional ray tracing, we'll do both of them, sort of join them in the middle. But for now, because of the way that this is the incoming ray. This is the ray parameter there that I'm intersected with, went this way. And so V is minus it. And then if we take V dot n, that's a scalar. N is a unit vector. This is what the projection of this is on the scalar. And what I want to do is I want to reflect this picture. Actually, this reflected ray is going up the same amount, but it's going over in the other direction. So basically, this component has to be made to go in the other direction, and this component has to stay the same. And a simple way to do that is to complete this parallelogram. Right? So this side is parallel to that side, and this side is parallel to that side, which means if this is the, what did I make? I didn't compute a lighting vector, did I? Shadow ray dot d. That's it. That's this vector. L is shadow ray dot d. And then if I add this vector to this vector, basically I'm going to get this piece, which I said was the projection, plus that piece. And so how do I want to think of that? That means that this unknown vector here is this much minus this much. Right? So that means the L that we're trying to find for the reflected ray, actually, this isn't shadow. I'm not thinking right. This is the reflected ray. I'm thinking more in terms of the Phong shading formula, which you need this for. Reflected ray. L is twice this scalar multiple, L dot n, which is that projection, multiplied by the vector n. So we have a scalar multiple of that vector which gets us to the top of this point of this parallelogram. It's a rhombus, right? These sides are the same, but this might not be a right angle here. And then we have to subtract the vector v, which is going to take us from this point down to this point, which is the head of this arrow, which is also a unit vector, the same length as this, but just flipped over. So minus v. So that's the formula for getting this L, which is the reflected ray direction. So you have to need the normal, say, as part of the shading record. So when we do next Monday how a ray intersects the object, we have to return the normal of that object as part of the shading information. So we can do this Whitted ray tracing with it. Okay, so the reason it's recursive, if we come back to this board, is because this thing calls the same routine. That's what's letting us get these multiple bounces. And at each bounce, if we have a diffuse computation, we do a shadow ray. Now, in the case of glass balls instead of metal balls, we could actually have a reflected ray and a refracted ray at each surface intersection, which means our ray tracing tree could sort of grow exponentially with the number of bounces if you have a lot of reflective and refractive objects. You could still actually have potentially infinitely many bounces. Say we had a mirror on that wall and a mirror on that wall, like the barber shop I went to as a kid did, and like certain ballet studios did. Well, you'll never be able to see infinite reflections because your head and your eye will always get in the way if they're perfectly aligned mirrors. But if you have an imaginary camera, which actually isn't intercepting the rays, you could have infinitely many bounces. So you have to have a way to stop the recursion. So in the more fancy ray tracing we'll get through in the end of the, further on the quarter, there's something called Russian roulette, which decides at each bounce whether to continue bouncing or just quit. But when you're writing this recursive ray tracing code for the first assignment, you can just pass an extra parameter which says how many bounces the ray has had so far. And if that number of bounces is greater than some preset limit, you just stop. Otherwise it could be a potential infinite loop in some particular viewing direction, and you'd never get to do anything else. So, are there any questions about the basic idea of the Whitted ray tracing? Okay, well, except for the ray-object intersection, which I've actually told you can use the code that I put online for, we have everything you need to do to start that first assignment. And I'll tell you, what's in that code next time anyway, for spheres and for triangles. So that's it for today.